Unit 11 Notes Part 5 covered two really big topics in acid-base chemistry. The first one being buffers. A buffer is any solution that can resist the change in pH for a limited amount of acid or base is added to it. The way that it does this is a conjugated acid-base pair is present um, in the solution. The number one solution where you'll see this in your life is your blood. Your blood contains several conjugated acid-base pairs. The reason why it has that is your pH of your blood has to stay really consistent in order for you to stay alive. If your blood gets too acidic or too basic, it results in death. So you have a bunch of acids and conjugated acid-base pairs hanging out in your blood. Little bit of acid gets into your blood, the bases will react. A little bit of base gets in there, the acids will react to keep your pH at a steady level. How much can actually be buffed out is called the buffer capacity. If you have a significant change in pH, then obviously you're beyond the buffer capacity. So for the problems with this, we're going to go through a couple different examples of this. So the first one says, what is the pH of a buffer prepared by adding 30 milliliters of 0.15 molar acetic acid to 70 milliliters of 0.2 molar sodium acetate? If you notice here, you have acetic acid that has HC2H3O2, and you have NaC2H3O2. So the common ion is acetate. The one piece of information I forgot to write into the problem here is Ka equals 1.7 times 10 to the negative fifth. The nice part about this is when you see Ka or Kbe given, you know that you're either dealing with an acid or a base. So the general form here of the acid is Ha plus water gives you H3O plus A minus. And we can do an ice chart here. So just like with the common ion effect that we did yesterday here, you can solve for the concentration of the acid and the concentration of the ion. The acid is going to be the acetic acid. The A minus is going to be the acetate from sodium acetate. The key to this problem here is you're adding a solution of both of them together. So even though you have 30 milliliters of 0.15 molar acetic acid and 70 milliliters of 0.2 molar sodium acetate, overall the total volume is 30 plus 70 or 100 milliliters, which is 0.1 liter. To solve for the concentration of HA, which is the acetic acid, and the A minus, which is the acetate ion, you first need to solve for how many moles of each one you have, and then divide it by the new total volume that it's in, which is the 0.1 liters. So for HA, which is our acetic acid, we have 0.15 moles per liter, because that's what molarity means. And it was originally in 0.03 liters, which is the 30 milliliters. And we're going to divide that by the new total volume, which is 0.1 liters. So that means that the new concentration, or the actual concentration of the acid, is 0.045. We can put that right here, 0.045. This is 0. And for A minus, the acetate ion, we had 0.2 molar in 70 milliliters, so 0.07, over the 0.1 again, same process that we were just doing. This is 0.14, so that's A minus. Then you just go through and do your ice chart the exact same way that you've been doing. You're going to lose this. You're going to gain X, gain X, gain X, and this is 0.14 plus X. You need to solve for X because you're asked for pH, so you need to know what H3O plus is. You're going to do your products over your reactants. Now if you notice, we have the minus X here, the plus X here. If you take our original concentration of our acid, 0.045, and divide it by Ka, 1.7 times 10 to the negative fifth, it's going to be greater than 100, which means we can get rid of those changes. So the minus X goes away, the plus X goes away, and you end up with X times 0.14 over 0.045 equals 1.7 times 10 to the negative fifth. Solve for X, which is your concentration of hydronium, and it's 5.46 times 10 to the negative 6. So then you can plug it into pH equals the negative log of that value, and solve, and it's 5.26 as your pH. The big new step here is just the solving for the concentration part before you plug them in, because you're mixing two volumes. Another way to deal with buffers is the Henderson-Hasselbalch equation. You can see the equation here, pH equals pKa plus log of the concentration of the base over the concentration of the acid. This is a good way to solve for the pH when you have different concentrations of conjugate acids and bases. If you notice, it has pKa equals the negative log of Ka. So if you know the Ka value, you can take the negative log of it, solve for pKa, and then plug into this equation. So the example here, if you do this, you are asked for what is the pH of this. Okay. In order to do that, you need pKa. You're given Ka in the problem of 5.6 times 10 to the negative 10th. So you need to take the negative log of that value, which is 9.25. And then you can plug in pH equals pKa, 9.25, plus log concentration of your base. The concentration of your base is 0.1. I know it's NH3 because bases will gain an H, and you have NH3, and then in here you have NH4, which is one more H, which makes that the acid. So this is 0.2. Solve for that, and it's 8.95. So the next thing on the back is acid-base titrations. You should have done this at the end of Chem 1, where you would have been taking an acid and adding a base, or take a base and add an acid. You usually use burettes in order to do this. You add it slowly, kind of 1 milliliter at a time, in order to find an equivalence point, and that's the point where the moles of acid equal the moles of base. Okay. So there's a bunch of different problems that you can do with this. I'm just going to show you one or two real quick. The first one says, what is the pH of a solution in which 15 milliliters of 0.1 molar NaOH has been added to 25 milliliters of 0.1 molar HCl? Remember, NaOH is a strong base, HCl is a strong acid, so they're going to completely break apart when you put them in water. What that means is that we can look at it as NaOH breaks apart into Na and OH. 1-to-1 ratio, so the concentration of OH originally is 0.1 molar. Same thing with the HCl. HCl will break apart into H and Cl. So the concentration of H, or hydronium, is the same thing as the HCl, so the 0.1 there as well. Now, what this means is you have 0.1 molar OH and there's 15 milliliters. So if we do 0.1 molar, which is moles per liter, times the volume that we have originally, 0.015, we had 0.0015 moles of OH to begin with. So we'll say it's of OH. Here we have 0.1 times 0.025, or 0.0025 moles of H3O+. Now, when you mix these two together, hydronium plus hydroxide gives you neutral water. So 0.0015 moles is going to cancel out with 0.0015 moles of hydronium, which means that you should have 0.001 moles of hydronium in excess, because there's 0.001 moles more that you started with. So that's the amount of moles of hydronium you have once this acid and base are neutralized together, divided by the volume. Well, we took 15 milliliters of sodium hydroxide and 25 milliliters of HCl and added them together. So we had 40 milliliters, or 0.04 liters, that this is dissolved in. So that means that our concentration of hydronium is 0.025 molar, because there's 0.001 moles per 0.04 liters. Now that we know the concentration of hydronium, we can solve for the pH by doing negative log of 0.025, which is 1.60. All that means is when the pH is 1.60, we have had the neutralization occur. All the bases reacted with the acid in this situation. Okay. The last two examples that are on here we'll do together in class on Friday. so that you can understand exactly where everything comes from. So just give the review a try. We'll go through that in class on Friday as well.